We will now go to Chapter 5, Reliability. The Cooder-Richardson formulas. These were developed by G. Frederick Cooder and M. W. Richardson on year 1937. These were made due to dissatisfaction with existing split-half methods. Most widely known formula is Cooder-Richardson Formula 20 or KR20, where test items are homogeneous. KR20 and split-half reliability estimates will be similar. However, KR20 is the statistic of choice for determining the inter-item consistency of dichotomous items. If items are heterogeneous, KR20 will yield lower reliability estimates than the split-half methods. So this is what the Cooder-Richardson Formula 20 looks like. The Cooder-Richardson Formula 20. An approximation can be obtained by the use of the 21st formula in the series KR21. Formula may be used if there is reason to assume that all items have approximately same degree of difficulty. Example, we have here 3 students who answered 3 questions. These questions are dichotomous. For example, these questions are graded whether they are incorrect or correct. So, in the Cooder-Richardson Formula 20, to make it easier, we grade the incorrect items as 0 and the correct items as 1. So what will happen here is that we sum it all up to get the P. So here we get 0.67, 0.67, and 0.33. So how do we get the Q? The Q is 1 minus P. 1 minus 0.67 is 0.33. So we have our Q here, 0.33, 0.33, and 0.67. So to get the PQ, we will multiply the P and the Q, 0.67 times 0.33. So all three answers will yield 0.22. Now we have to sum it all up to get the 0.66 answer. Numerous modifications of KR formulas have been proposed. One variant that has received the most acceptance is coefficient alpha. Coefficient alpha was developed by Cronbach in year 1951. Coefficient alpha may be thought as a mean of all possible split-half correlations corrected by Spearman-Brown formula. This is used on tests containing non-dichotomous items. So this is the formula for the coefficient alpha. As you can see, we have quite the similarity with the Cooder-Richardson formula, except for this part. Both the KR20 and the coefficient alpha can produce estimates of reliability with just one test. Both can produce estimates of reliability using dichotomous items. However, only coefficient alpha can produce reliability estimates based on polytomous items. You may hear it as coefficient alpha 20, the latter as referenced KR20. Coefficient alpha is a preferred statistic for obtaining estimate of internal consistency reliability. Pearson R may range in value from -1 to 1. As we can remember, Pearson R estimates the strength of linear relationships between two variables where if R is 0, it means no relationship. If R is -1, negative correlation. If R is +1, it stands for positive correlation. However, coefficient alpha ranges from 0 to 1, where 0 means no consistency, 1 means perfect consistency, and if it's somewhere in between, like 0.70, this means that 70% of variance is reliable while 30% is called the error variance. Variation of the formula has been developed for use in obtaining an estimate of test-retest reliability. This formula yields estimate of means of all possible test retest split half coefficients, widely used as measure of reliability because it requires only one administration of the test. Let's move on to the average proportional distance or APD. This was developed by Sturman on year 2009. This focuses on the degree of difference that exists between the item scores rather than focusing on the degree of similarity between scores on items of a test. First, we have to calculate the absolute difference between scores for all the items. Second, average the difference between scores. Third, obtain APD by dividing the average difference between scores by the number of response options on the test, minus 1. So as an example for the APD, we will use a free item test of extroversion and a 7-point scale. So for example, in item number 1, you put in 4, neither agree nor disagree. For item number 2, you put in 5, agree. For item number 3, you put in 6, strongly agree. So now we have to get the difference between the test items. For item number 1 and number 2, 4 and 5, the difference is 1. For item number 1 and 3, 4 and 6, the difference is 2. For item number 2 and 3, 5 and 6, the difference is 1. So, the average proportional distance after calculating this would be 0.22. So what does 0.22 stand for? For the interpretation of APD, zero point 0.2 or lower means excellent internal consistency. 0.25 to zero point 0.2 is the acceptable range, while 0.25 is suggestive of problems with internal consistency of test. APD is not connected to the number of items on a measure, which makes it advantageous over Cronbach alpha, because Cronbach's alpha will be higher when a measure has more than 25 items. Indices of reliability provide an index characteristic of particular group of test scores, not the test itself. Measures of reliability are estimates, and estimates are subject to error. Measures of interscorer reliability. This was variously referred to as scorer reliability, judge reliability, observer reliability, and inter-rater reliability. The degree of agreement or consistency between two or more scorers with regards to a particular measure. To try not to be a product of individual biases and idiosyncrasies in judgment, we can have at least one other individual observe and rate the same behavior. If consensus is demonstrated, more confidence regarding accuracy of the ratings and conformity will be established on the rating system. This is often used for coding nonverbal behavior. The simplest way of determining the degree of consistency is to calculate a coefficient of correlation, referred to as a coefficient interscorer reliability. Approaches to estimation of reliability are test-retest, alternate or parallel forms, internal or inter-item consistency. A published study by Milowski et al. 2015 highlighted the substantial influence that differences in method can have on estimates of inter-rater reliability. High levels of diagnostic inter-rater reliability are vital for the accurate diagnosis of psychiatric and psychological disorders. First, diagnostic reliability must be acceptably high to accurately identify risk factors for a disorder that are common to subjects in a study. Second, low diagnostic reliability can also lead to improper information regarding how a disorder changes over time. Estimates of DSM-5 inter-rater reliability were largely derived using the audio recording method. One clinician interviews patient and assigns diagnosis. Then, a second clinician who does not know what diagnoses were assigned listens to an audio recording of the interview and independently assigns a diagnosis. Strength of recent versions of DSM is that disorders can be diagnosed with a high level of inter-rater reliability, especially when semi-structured interviews are used. In test-retest method, separate independent interviews are conducted by two different clinicians, with neither clinician knowing what occurred during the other interview. These interviews are conducted over a time frame short enough that true change in diagnostic status is highly unlikely.
making this method similar to the dependability method of assessing reliability. This provides a more meaningful, realistic, and valid estimate of diagnostic reliability. Diagnostic reliability using audio recording method was very high and would be considered excellent by traditional standards. Moreover, estimates of diagnostic reliability were equivalent or superior to previously published values for the DSM-5. However, estimates for test-retest reliability were substantially lower and would be considered fair by traditional standards. The results demonstrate the substantial influence that method has on estimates of diagnostic reliability even when other factors are held constant.
The purpose of reliability coefficient. For single administration, estimate of internal consistency. If it's for breaking down error variance into its parts, number of reliability coefficients would be calculated. For example, in this pie graph, 5% accounts for an identified error. This may be transient error or the test taker's feelings, mood, or mental state over time. Now let's move on to the nature of the test. Homogeneity versus heterogeneity. Homogeneous tests are designed to measure one factor. Homo means uniform throughout. These have high degree of internal consistency. Heterogeneous tests are designed if variables are mixed. Heterogeneous tests estimates might be low. Dynamic versus static characteristic. Dynamic is a trait, state, or ability presumed to be ever-changing as a function of situational and cognitive experiences. An example of this would be anxiety of a student as he awaits for his name to be called in an oral recitation. Static, for example, is relatively unchanging like the student's intelligence. Restriction or inflation of range. If the variance is restricted by sampling procedure, the resulting correlation coefficient tends to be lower. If the variance is inflated by sampling procedure, the resulting correlation coefficient tends to be higher. Speed test versus power test. Power test. Time limit is long enough to allow test takers to attempt all items. Some items are so difficult that no test taker is able to obtain a perfect score. In power tests, it is arranged increasing in difficulty and it tests the knowledge of the test taker. These scores are based on the number of items answered and answered correctly. Speed test. Items contain uniform level of difficulty, so when given generous time limits, all test takers would be able to complete all items correctly. So in speed tests, there are easy items and the scores are based on the number of questions he attempted to answer. Criterion reference tests are designed to provide an indication of where a test taker stands with respect to some variable or criterion. This contains materials mastered in a hierarchical fashion. For example, a pilot is being tested on his knowledge on machineries. So, this can be based on master failed to master kind of criterion. The true score model of measurements and alternatives to it. The classical test theory is the most widely used and accepted model in the psychometric literature today because of its simplicity and notion that everyone has a true score. The true score is a value according to CTT that genuinely reflects an individual's ability or trait level as measured by a particular test. Its assumptions allow for its application in most situations, compatibility, and ease of use with widely used techniques. The disadvantages of CTT is its assumption concerning equivalence of all items on a test and the length of tests. Assumptions inherent in CTT favor development of longer rather than shorter tests. Domain sampling theory seeks to estimate the extent to which specific sources of variation under defined conditions are contributing to the test score. The test's reliability is conceived of as an objective measure of how precisely the test score assesses the domain from which the test draws as a sample. It is better known today in one of its many modified forms as generalizability theory. Generalizability theory was developed by Lee J. Cronbach and his colleagues in 1972. A universe score replaces that of a true score. A person's test score varies from testing to testing because of variables in the testing situation. Universe is collection of possible measures of same kind, but limits of collection are determined by the investigator's purpose. Your universe score on May 5 is not equal to your universe score for the whole month of May. If there's only a single observation, it will be generalizing. If observed scores from procedure agree closely with us, we say the observation is accurate, reliable, or generalizable. This Cronbach encouraged test developers and researchers to describe the details of the particular test situation or universe leading to a specific test score. Universe is described in terms of facets. Given the exact same conditions of all the facets in the universe, the exact same test score should be obtained. This is called the universe score and is analogous to a true score. A generalizability study examines how generalizable scores from a particular test are if the test is administered in different situations. The influence of particular facets on the test score is represented by coefficients of generalizability. In the decision study, developers examine the usefulness of test scores in helping the test user make decisions. Designed to tell the test user how the test score should be used and how dependable those tests are as basis for decisions. The G theory is used for evaluating the dependability or reliability of behavioral measurements. Item response theory or IRT provides a way to model that a person with X ability will be able to perform at a level of Y. This means that a person with X amount of personality trait will exhibit Y amount of that trait on a personality test designed to measure it. IRT measures how individuals respond to individual items on psychological and educational tests. Item response theory or IRT. A synonym for IRT in the academic literature is latent trait theory. This is because often the construct being measured is physically unobservable or latent, and because construct being measured may be a trait. Discrimination signifies the degree to which an item differentiates among people with higher or lower levels of the trait, ability, or whatever it is being measured. Different IRT models exist to handle data resulting from the administration of tests with various characteristics and in various formats. Example, I am able to walk from room to room. I require assistance in standing, walking, and sitting. I am able to jog 1 mile per day. In CTT, this may be measured as 1 for mobility or 0 for lack of mobility. So, 1 for the first sentence, 0 for the second sentence, and 1 for the third sentence. However, in IRT, these are measured based on the differential weights assigned to them. So, the first sentence may be given more points or may earn more points than the second sentence. Or the third sentence may be able to earn more points than the first sentence. In CTT, no assumptions are made about the frequency distribution of test scores. Such assumptions are inherent in latent trait models. Rasch model, for example, developed by George Rasch, is reference to an IRT model with very specific assumptions about the underlying distribution. The Rasch model is a trade-off between A. Respondent's ability, attitude, and personality, and B. The item difficulty.
Dr. Bryce B. Reeve uses skills and training to design questionnaires and studies to capture the burden of cancer and its treatment on patients and their families. He designs HRQOL types of questionnaires, or those that measure a person's health-related quality of life. It is a multidimensional construct capturing such domains such as physical functioning, mental well-being, and social well-being. Different cancer types and treatments for those cancers may have different impact on the magnitude and which HRQOL domain is affected. The challenge is to develop valid and precise measurement tools that capture changes in patients' lives. Psychometrically strong measures also allow us to evaluate the impact of new behavioral or pharmacological interventions developed to improve quality of life. Dr. Reeve used qualitative methods like focus groups and cognitive interviewing to make sure that they have captured the experiences and perspectives of cancer patients and to write questions that are comprehensible to people with low literacy skills or people of different cultures. They use quantitative methods to examine how well individual questions and skills perform for measuring the HRQOL domains. They use classical test theory, factor analysis, and item response theory to first develop and refine questionnaires, second, identify the performance of instruments across different age groups, males and females, and cultural or racial groups, and third, to develop item banks which allow for creating standardized questionnaires or administering computerized adaptive testing. We use IRT models to get an in-depth look to how questions and scales perform in their cancer research studies. Differential item function, or DIF, is a key methodology to identify biased items in questionnaires. We use IRT modeling to examine diff in item responses on many HRQOL questionnaires. We use IRT to look at unadjusted and adjusted IRT scores to see the effect of the diff item without removing the item from the scale if the item is deemed relevant. The greatest challenges he found to greater application or acceptance of IRT methods in healthcare research are the complexities of the models themselves and lack of easy-to-understand resources and tools to train researchers. Many researchers have been trained in CTT statistics, are comfortable in interpreting these statistics, and can use readily available software to generate easily familiar summary statistics, such as Cronbach's coefficient or item total correlations. In contrast, IRT modeling requires an advanced knowledge of measurement theory to understand the mathematical complexities of the models, to determine whether the assumptions of the IRT models are met, and to choose the model from within the large family of IRT models that best fits the data and the measurement task at hand. In addition, the supporting software and literature are not well adapted for researchers outside the field of educational testing.
The standard error of measurement, or SEM, also known as the standard error of a score. This provides a measure of precision of an observed test score. This provides an estimate of the amount of error inherent in an observed score or measurement. The relationship between SEM and reliability of a test is inverse. This is the formula for the standard error of measurement. So because of this, we can predict what would happen if a test taker were to take additional tests. If the standard deviation is constant, the smaller the SEM will be, the more reliable the test will be. As the reliability coefficient increases, the SEM decreases. The SEM is important in establishing the confidence interval. Confidence interval is range of scores that is likely to contain the true score. For example, a 22-year-old test taker takes a full-scale IQ test and scored 75. The SEM is 2.37. The test user is 95% confident that the true score lies from 70 to 80. So, with this formula, the final answer will be 75 plus minus 4.645. 4.645 if rounded will be 5. 75 plus 5 is 80. 75 minus 5 is 70. Standard error of the difference is a statistical measure that can aid a test user in determining how large a difference should be before it is considered statistically significant. The standard error of the difference between two scores can be the appropriate statistical tool to address three types of questions: test 1 versus test 2, test 1 versus someone else's test 1, and test 1 versus someone else's test 2. For example, we have 5 different sets of data. In 5 different sets of data, we have 5 different means. Then we get the mean of all those means. The standard error is also called the standard deviation of means. So when we are comparing scores achieved on different tests, it is essential that the scores would be converted on the same scale. And if we substitute the reliability coefficients for the standard errors of measurement of the separate scores, the formula becomes, for example, a safety-mindedness test. Moe scored 125 and Larry scored 134, with a standard deviation of 14 and reliability of 0.92. For any standard error of the difference, we can be 68% confident that two scores differing by one standard deviation represent true score differences, 95% confident that two scores differing by standard deviation represent true score differences, and 99.7% confident that two scores differing three standard deviation represent true score differences. So with these results, we are 68% confident that two scores differing by 5.6 represent true score differences, 95% confident that two scores differing by 11.2 represent true score differences, and 99.7% confident that two scores differing by 16.8 represent true score differences. Now let's go back to Larry and Moe's test results. We have 135 minus 124, the difference is 9. And we want to be 95% confident about it. But 9 is still way too far from 11.2. It is not large enough difference to conclude with 95% confidence.